In this lesson, we're going to talk about linear functions. And for a linear function, they're going to have the form of f at x equals m times x plus b. Here we have the slope equal to m, and our y-intercept is at the point 0b. We've studied the equation of lines before, and as long as we do not have a vertical line, any linear equation is also a linear function. And we have the word line in the name, so we should know what the shape of these functions looks like. Let's look at an example. If we have a company car that cost $28,000 and it has a straight line depreciation for 7 years, we can write the equation of the value of the car, or the function that will model its value, by using a linear function. And the key here is that it was straight line depreciation. And what that means is that after 7 years, the company values the car at $0. And so it starts out at $28,000 and after 7 years has a value of $0. And so we know that the slope is negative 4,000 and the y-intercept is 28,000. So the slope came from 28,000 divided by 7 years, so it decreases by $4,000 each year. And if we were to draw a graph, our input is the year, our output is the value of the car. We have the y-intercept at the point 28,000. We have an x-intercept at the point 7, 0. Draw a straight line between our points, and there's the value of the car each year. If we wanted to find the value after 2 years, we know that it is 8,000 less than 28,000, so that'd be 20,000. So a second application that we would see using linear functions has to do with supply and demand. So the supply is the quantity that a company is willing to produce for a given price. So let's say that the supply is 60p minus 900, and the demand is the amount that the consumers are willing to buy for a given price. So P is the price of the product. If we were to graph these two functions, supply only makes sense when the price is at least $15. We get the point 15, 0. They're not going to create any of the product if it doesn't sell for at least $15. And the demand has a y-intercept of 0, 2,850, but it's a negative slope, so I know it's decreasing from left to right. The point where supply equals demand is called the equilibrium point. And so the price where they are equal would be called the equilibrium price, and we are trying to solve S at P equals D at P. So when does supply equal demand? And we can do this algebraically, and we would find that our equilibrium point is the point 50, 2100, which means when the price is $50, the company is willing to create 2,100 of the products, units of the product, and the consumer is willing to purchase 2,100 of the product. So everything produced would be sold, which seems an ideal situation. The last application we want to do is comparing linear functions. So when is one line bigger than another line? And here we are looking at the y values, or the output values. So when are the outputs for f at x bigger than g at x? So let's just start with the graph of two lines. F at x is going to go through the points 0, -2, and the point 2, 3. And g at x is going to go through the points 0, 2, and the point 2, 3. So we see that they intersect at the point 2, 3, and we want to know when is f at x greater than or equal to g at x. Well, f at x equals g at x when x equals 2. But if we look at x values bigger than or equal to 2, f at x is bigger than g at x. And one way I like to look at this is to compare points with the same x value. So this means, oops, that's a typo. We want bigger y values. Let me erase this. Bigger y values. So if I look at the point where x equals 4 on f at x, I get the point 48. And if I look at the point where x equals 4 on g at x, I get the point 44. And the y value is bigger for f at x than g at x. Another way to do this is drawing a vertical line. And to draw a line from f at x to g at x, I have to go down. So that makes f at x bigger. And if you look at other places, like here when x equals 3, we have to go down from f at x to g at x. If I go smaller than 2, I need to go up from f at x to g at x. So here in this region, we have f at x less than or equal to g at x. And that's when x is less than or equal to 2. So I use the vertical line from f at x to g at x to help me solve the inequality, but we could also do this algebraically. We know that f at x equals 5/2 x minus 2 because we could find its slope, and we knew its y-intercept was 0, -2. And g at x equals 1/2 x plus 2. And so now we're just solving 5/2 x minus 2 greater than or equal to 1/2 x plus 2. And we get 4/2 x is greater than or equal to 4. So I added 2 to both sides, and I subtracted 1/2 x from both sides. Simplifying the 4/2 x, we have 2x greater than or equal to 4. And dividing both sides by 2, we get x greater than or equal to 2, which is exactly what we had before by looking at the graph.